It's the quantumest course in the whole wide world. It's Physics 402.
Hello and welcome to another episode of Physics 402. I'm your host, Professor Mark, and today we're going to be talking about physics at finite temperature. And so specifically, I want to think about a collection of atoms or molecules, and we can just imagine they're in some kind of a cavity that is being kept at some temperature T. And we want to understand what is the physics inside that cavity. And so the first thing we can talk about are the atoms or molecules themselves. And because we're at finite temperature, they will typically have some kinetic energy. They'll be moving around, and their velocities will be given by this Maxwell-Boltzmann distribution of velocities. You can look that up. I'm not going to talk about it today. What I want to focus on is what are the quantum states of those individual atoms or molecules. And so what we're imagining is that each of those has some energy eigenstates that we're going to call EI as usual. And so because these molecules are interacting with each other and interacting with thermal radiation that's in the cavity, then those are typically going to be in various different energy eigenstates. And one of the basic results of statistical mechanics or thermodynamics is that the probability that we're going to find ourselves in the energy eigenstate EI, so I'll call that PI, is proportional to what's called the Boltzmann factor. It's e to the minus EI divided by KT. And so what that means is that higher energy states are less likely, but the lower the temperature is, the more that those higher energy states are suppressed. And so, for example, if we think about an atom or a molecule with a collection of eigenstates of possible energies, and then we think about all the atoms in the box, then we might find at very low temperatures that a lot of them are in their ground state, and maybe a couple of them are in some of the excited states. But then if we look at very high temperatures, we're going to have a lot of atoms in those higher energy states. It'll be more spread out, still typically more in the ground state. Okay, and so that's what this probability tells us. Of course, the probabilities all have to add up to 1, and so if we actually want to write a formula for the probability as an equality, then we have to put some constant out front, and it's conventional to call that 1 over z, where z is the sum over all of the states of the Boltzmann weight, and that's known as the partition function. But for our purposes, what we'll mostly be using later on in the later videos is this fact that tells us the relative likelihood of any one of those atoms or molecules being in this state with energy EI. Okay, so the atoms and the molecules are not the total story, because we also always have some electromagnetic radiation in the cavity that is characteristic of being at a temperature T. And you can think of that as being produced, say, by the walls of the cavity. Those are warm. They're going to produce, say, infrared radiation if we're talking about ordinary room temperatures. And we would like to know, well, how much radiation is there, and what are the frequencies of that radiation? And so the way that we can do that is to define a function, which I'm going to call Rho of Omega. And so Rho of Omega, it tells us the density of energy of radiation for certain frequencies. So specifically, we wanted to find this Rho of Omega such that if we take Rho of Omega and multiply it by some small range of frequencies, then this gives the energy of the electromagnetic radiation in an interval between omega and omega plus d omega. Okay, so there's a certain amount of energy with frequencies in that interval, and that is given by this rho of omega times d omega. Another way to think about that is that we could make a graph of rho of omega. So here's rho of omega, there's omega, and here's our graph. And so a way to interpret that graph is that if I want to know how much energy, what's the energy density of radiation, and I want to add up the energy of all the electromagnetic waves whose frequencies are between omega 1 and omega 2, then what I need to do is just take the area under that graph, and that will be the total energy in that interval. Okay, so the special thing about being at finite temperature in equilibrium is that there's a particular formula for this energy density, and that's called the Planck Formula. It was derived by Max Planck, and the formula tells us that rho of omega is given by some constants. I'll write them down: h bar over pi squared c cubed, and then times omega cubed over e to the h bar omega over kt minus 1. Okay, so that's some very particular function of omega, and what you'll find is that, okay, it looks something like this, but as you increase the temperature, one of the things that happens is that the peak frequency moves higher and higher, so the hotter it is, the higher the peak frequency, or the shorter the peak wavelength of that radiation, and then the amplitude, or I should say the size of the function rho of omega, which is telling us the amount of radiation there, the total energy density, that increases at all the wavelengths. And so the higher the temperature, the more energy you have in electromagnetic radiation. Okay, and so in our later videos, where we're going to use this to derive the spontaneous transition rate for transitions in atoms and molecules, the main thing we're going to need about this picture is that if we have atoms in a box, in a cavity with a temperature T, that the energy density in radiation is given by this Planck formula, and that the relative probabilities for each of those atoms to be in their various energy eigenstates is given by this Boltzmann formula, that the probability is proportional to e to the minus e over kt.